All right, let's dive into something that we see all around us every day. We rarely stop to think about it, though, and that's matter. And we are going to be taking a chapter from a science textbook, I think middle school level. And I think even if you aced, science class back in the day, we're going to uncover some really cool things.
It is fascinating how even the most fundamental concepts that we encounter can actually hold hidden complexities. We often take matter for granted, but when you actually delve into its nature and its properties, it's a whole new world.
Yeah, and that's exactly what we're going to be doing. We're going to be unpacking what matter is, how it behaves, and the ways it can change from solid to liquid to gas. But before we get into all that, here's a question. Have you ever thought about how something as solid as a rock can actually be mostly empty space?
It's mind-boggling, isn't
Yeah.
it? It's just the way that those tiny particles are arranged and they interact, and it creates this illusion of solidity. But at its core, it's a dance of energy and space.
Okay, so
Yeah.
let's start off by defining matter, and the textbook lays out a pretty classic definition. It's anything that occupies space and has mass. So basically, if you can touch it and it takes up space, it's matter. But what I found really interesting is that even ancient cultures were trying to figure out what matter was made of.
Absolutely. The Indian Panchtattva philosophy with its five elements: air, earth, fire, sky, and water. And the ancient Greek concept of four elements, right? Earth, air, fire, and water, show how humans have, always sought to understand the building blocks of our world.
It is amazing to see how those ancient philosophies, though they were different from our modern scientific understanding, they were grappling with the same fundamental questions. But how did we go from those elemental ideas to the concept of tiny invisible particles making up everything?
That's where scientific observation and experimentation come in. The textbook describes some simple but very effective activities that demonstrate the particulate nature of matter, like dissolving salt or sugar in water. Where does the salt go? It seems to disappear, but it's actually dispersing into particles that are too small to see.
So it's like those salt particles are infiltrating the water, finding their way into those spaces between the water molecules.
Exactly. Another activity involves diluting potassium permanganate in water, and
Yeah.
you can dilute it multiple times, and the water remains colored, um, suggesting that the original crystals were composed of a mind-blowing number of incredibly tiny particles.
Millions of particles in a single crystal. Try to picture that just boggles my mind. And they're not just sitting still either, right? The textbook mentions the scent of incense spreading through a room as evidence of particle movement.
That's right. The particles that make up matter are constantly in motion. They have kinetic energy, and the hotter the temperature, the faster they move. It's like a microscopic dance floor. Turn up the heat, and the particles get more and more energetic.
I'm starting to see how this constant motion and energy plays into those different states of matter. So let's
Mhm.
talk about solids. Things like rocks, ice, wood. They're rigid, they hold their shape, and they have a fixed volume. So how do those super tiny, constantly moving particles create something that feels so solid?
In a solid, the particles are very tightly packed together, vibrating in place but not moving freely. The forces of attraction between those particles are strong,
Mm.
holding them in that fixed arrangement. Think of a highly organized marching band. Everyone's in their place, but there's still a lot of energy and movement within that structure.
Okay, so those tightly packed vibrating particles are what create that illusion of solidity. But then we have liquids. And liquids are fluid and they take the shape of their container. So what's going on with those particles in a liquid?
In a liquid, the particles they're still close together, but they have more freedom, to move around,
Mm.
to slide past each other. The forces of attraction are weaker than in a solid, allowing the liquid to flow. Imagine a crowd of people moving through a busy street. They're bumping, they're jostling, but they're still relatively close together.
So those particles in a liquid are like a crowd navigating a rush hour commute, always in motion but staying connected. And then we have gases which are all over the place. They expand to fill any container. What makes gas particles so different?
In a gas, the particles are much farther apart, and they're moving rapidly in random directions. The forces of attraction are very weak, so the particles have a lot of freedom, and can spread out to fill any space, think of those particles as being in a massive rave,
Yeah.
bouncing off of each other in the walls with tons of energy.
So we've been talking about how those particles behave in solids and liquids and in gases, but there's another thing that can totally change the game, and that's pressure. I mean, we all know what pressure is. You inflate a tire, you feel it when you dive deep underwater, but how does it actually affect whether something is a solid or a liquid or a gas?
It all comes down to the space between those tiny particles.
Yeah.
Remember how in gas those particles are spread out and they're moving freely? Well, when you apply pressure, you're essentially squeezing those particles closer together. It's like taking that massive wave we were talking about and just shrinking the dance floor.
So are you saying that if you squeeze a gas hard enough, you can actually force it to become a liquid? That seems kind of counterintuitive.
It might seem that way, but it's a fundamental principle. Think about those compressed gas cylinders you see for propane or for oxygen. They contain a huge amount of gas squeezed into a really small space, and that high pressure forces the gas into a liquid state.
Wow. So that's how they pack so much gas into those cylinders. It's amazing how much pressure can change the game. But what about going the other way? Can reducing pressure make something more gassy?
Absolutely. The textbook mentions dry ice, which is solid carbon dioxide. When you release the pressure on dry ice, it goes straight from a solid to a gas. It sublimates. Instead of melting into a liquid first, it just skips that step entirely.
So pressure can make things more solid or more gassy. This is definitely making me think about matter in a whole new way. But the chapter also talks about evaporation, which is a whole other way that matter changes states, and it doesn't even require boiling.
Evaporation is happening all around us, all the time. It's how puddles dry up. It's how wet clothes eventually get dry. It's even how we cool down when we sweat. It's like this stealthy phase change that's always at work.
Okay, so how does this stealthy phase change work? The textbook says it has something to do with particles escaping from the surface of a liquid.
That's right. Even though a liquid might not be at its boiling point, some of those particles at the surface, they have enough energy to break free from the forces that are holding them in that
Right.
liquid state. They gain enough energy to escape and become a gas.
So it's like those surface particles they're getting this sudden burst of energy. They're just launching themselves up into the air. But why just the ones at the surface? Are they getting special treatment?
The particles at the surface, they have fewer neighbors holding them back. Think about it. The particles in the middle of that liquid, they're surrounded by other particles on all sides. But the ones at the surface are only bound on one side, so they have a better chance of escaping.
Ah, so they've got less pure pressure to stay in that liquid state. I like that analogy. But the textbook also mentions that certain things can affect the rate of evaporation. What are some of those factors?
Well, one of the most obvious is surface area. If you spread out your wet clothes to dry, you're increasing the surface area of that wet fabric that's exposed to the air, giving more water molecules a chance to escape.
So more surface area equals more escape routes for those adventurous particles. Makes sense. What about temperature? Does that play a role?
Definitely. Higher temperatures mean the particles have more energy, so more of them are going to have enough energy to escape. That's why puddles dry up faster on a hot day. It's like turning up the heat at that rave. More particles are going to get energized enough to jump off the dance floor.
Yeah. Okay. More heat, faster evaporation. What about humidity? Does that affect things?
Absolutely. If the air is already saturated with water vapor, if it's humid, there's less room for more water molecules to evaporate. It's like that rave is already packed. No room for more party goers.
So dry air equals faster evaporation. Makes sense. Is there anything else that can speed up or slow down evaporation?
Wind speed can play a role. Wind carries away the water vapor that's already evaporated, making room for more to escape. It's like having a fan at that rave, blowing away those escape particles to make room for others.
That's a great analogy. We've covered a lot of ground here, pressure, evaporation, these crazy escaping particles. But there's one more thing that really caught my attention in the chapter, and it's the fact that evaporation can actually cool things down. How does that work? Are those escaping particles taking the heat with them?
You got it. The particles that evaporate are the ones with the most energy. And when they escape, they take that energy with them, leaving the remaining liquid cooler. It's like the most energetic dancers leaving the rave. It lowers the overall energy level and makes it feel, cooler for everyone left behind.
So we've been, unpacking some really, really cool stuff about, particles, pressure, evaporation, all these things that affect how matter behaves. But I want to talk about a substance that's kind of a rule breaker, and that's water. We all know water, we use it every day, but it has some unique properties that the chapter dives into.
Water is essential for, life as we know it, and it's, an unusual behavior is a big part of that. One of the most fascinating things about water is its density. Normally substances are most dense in their solid state. Think about a rock. The particles are packed tightly together, making it heavy and compact. But water flips the script on that.
Right. Ice floats, which means it's less dense than liquid water. It seems totally backwards.
It does, but this peculiar property is crucial for life on Earth. If ice were denser than water, lakes and oceans would freeze from the bottom up.
Yeah.
And that would have, devastating consequences for aquatic life.
So those ice cubes clinking in my glass are actually a testament to a life-sustaining anomaly. That's pretty amazing.
Yeah.
But how does water pull off this density trick? The chapter mentions something about hydrogen bonds.
It all comes down to the shape of the water molecule
Hmm.
and its ability to form these hydrogen bonds. In liquid water, the molecules are, close together, but they're constantly moving and breaking those hydrogen bonds. When water freezes, those hydrogen bonds become more rigid, and they form this crystalline structure. And that structure actually has more space between the molecules than in liquid water.
So it's like those water molecules they're holding hands in liquid water, but when they freeze, they kind of spread out a bit, creating those spaces that make ice less dense.
Exactly. And this unusual density is just one of water's many unique properties. Its ability to dissolve a wide range of substances, its high surface tension, its role in regulating temperature are all vital for life as we know it.
Well, this deep dive has really, really given me a whole new perspective on matter. We started with a simple definition, and then we explored the world of particles, states of matter, phase changes, pressure, evaporation, and even the quirky behavior of water. It's incredible how much is happening at the microscopic level that we never even think about.
It really highlights the interconnectedness of scientific concepts and how even the smallest particles can have a huge impact on the world around us.
Absolutely. So next time we see, ice melting or we feel the coolness of evaporation, we can remember that incredible dance of particles that's making it all happen.
And hopefully this deep dive has sparked a curiosity to keep exploring the fascinating world of science. There's always more to discover.
Couldn't have said it better myself. Thanks for joining us on this journey into the mysteries of matter. We'll catch you next time, fellow knowledge seekers.